Here we're going to look at a problem from the International Math Olympiad. This is from the 1999 edition, and it's question 4. So our goal is to find all pairs of natural numbers x and p such that p is prime and x is less than or equal to 2p, and then finally x to the p minus 1 divides p minus 1 to the x plus 1. So this is like kind of a complicated looking thing, but as we'll see, we'll be able to simplify it a bit. Okay, and I've got 3 hints to maybe try before we look at a full solution. And the first hint is to consider all of the small obvious cases first. Most especially the one where the prime is equal to the number 2. And often when you're solving problems regarding prime numbers, something different happens when the prime is equal to 2 versus a larger odd prime. And then my next hint is to think about Fermat's little theorem. That says that if p is prime and p does not divide a, then a to the p minus 1 is congruent to 1 mod p. And then finally, there's this thing called Bézout's identity, which follows from the Euclidean algorithm via something called the extended Euclidean algorithm. And that says that for all natural numbers m and n, there exist integers x and y such that mx plus ny is equal to the GCD of m and n. In other words, the GCD of 2 natural numbers can be written as a linear combination of those 2 natural numbers. Okay, so maybe give this problem a go with these hints, and we'll come back with a full solution. So hopefully those hints were helpful. Now we're going to look at a full solution, starting with the first hint, which was to look at the small obvious cases first. So the first case that I want to look at is what happens if x equals 1? Well, 1 is a natural number. P can't be 1 because p is prime, and we know that 1 is not a prime number, but x could most definitely be 1. So let's see if we get some solutions out of that. So let's see, if x is equal to 1, then this condition down here collapses a lot. So let's look at this condition. So I'll just call it the condition. Becomes the following. So we have x to the p minus 1, so that's going to be 1 to the p minus 1 divides p minus 1 to the x plus 1. But x is equal to 1, so that's p minus 1 to the first power. But this is the same thing as the condition that 1 divides p. But now this is obviously true for all primes. So let's maybe go ahead and write that down. So true for any prime p. And so that actually gives us a whole family of solutions, an infinite family of solutions given by 1 comma p. So we'll write that down. So 1 comma p, I'll say represents a solution for all primes p. Great. So now let's look at the next case maybe, which was the one that I alluded to in the hint, which was when that prime number was equal to 2, because often when primes are equal to 2, you have to work on those kind of individually from larger odd primes. So let's maybe look at the case when p equals 2 and see what the condition becomes in this case. So the condition is the following in this p equals 2 case. So we'll have x to the 2 minus 1, so that's just x, divides, so now we have p minus 1, so that's going to be 2 minus 1 to the x plus 1, but that's just going to be equal to 2. So we know that x divides 2, but given the fact that 2 is prime, that tells us that x equals 1 or x equals 2. So notice the solution x equals 1, p equals 2 is contained in this up here because 2 is definitely a prime. So we get a new solution out of this as well, and that solution is x equals 2 and p equals 2. So I'll just go ahead and write that down. So 2 comma 2 is also a solution. And now the next thing that I want to check is that, well, what if x equals 2? Can we get a solution for other primes? And in fact, you can't. So if x equals 2, then p also must be equal to 2. And I'll leave that for you guys to check, but that's not too hard to check, doing the same kind of thing that we did right here. Which means as long as x and p are less than or equal to 2, we only have this solution and then the 1, 2 solution. So we've got this infinite family of solutions at this point, and then we have this 2, 2 solution. So I'll go ahead and clean up the board, and then we'll look at the case when we have p is a prime bigger than or equal to 3. So we were just playing around with the small cases, and we saw that 1, p represented a solution for all primes p. And furthermore, p equals 2, x equals 2. In other words, 2, 2 was also a solution. And this was the only solution when p was equal to 2, and I left it to you guys to show that that was the only solution when x equaled 2 as well. So that means that we can move on to supposing that x and p are bigger than or equal to 3 and see what solutions we get out of that. So now notice, if x and p are bigger than or equal to 3, that means that p is an odd number, because the only even prime is the number 2. That's what makes it kind of stand apart from all the primes when we're doing these kind of calculations. But now if p is odd, notice that we've got p minus 1s floating around here, so we might want to look at the parity of p minus 1. That tells us that p minus 1 is even. But notice over here we have p minus 1 to the x, but any even number to an exponent is also even. So that tells us that p minus 1 to the x is also even. But that means if we add 1 to it, we'll get something that's odd. So in other words, we have p minus 1 to the x plus 1 is odd. Okay, great. But notice that we have x to the p minus 1 divides this thing right here. That's kind of our given setup condition. So that means x to the p minus 1 divides an odd number. But that means it's impossible for x to the p minus 1 to be even. Because if x to the p minus 1 were even, you'd have an even number dividing an odd number, but that's impossible to happen. So in other words, we know that x to the p minus 1 is also odd. But again, the only time an exponent of a number is odd is if that underlying number is also odd. So we know the parity of x now, and we can say that x is most definitely odd. Great. So we know that p is odd because it's a prime number bigger than or equal to 3. And now we know that x is odd. Now the next thing we want to think about is using Fermat's little theorem. And we want to look over here and see, can we use it on the left-hand side or on the right-hand side? So I'll let you guys play around with one or the other, but what you'll find out is it's not super useful to use on the left-hand side, so we might want to use it on the right-hand side. But the problem with the right-hand side is that our exponent here is x, and we don't know so much about x. But one thing that we do know about x is that it can be factored into primes, because all natural numbers can be factored into primes. So let's maybe go ahead and do that. And let's, since we've got a choice, take maybe the smallest prime that factors x. So let's let q be the smallest prime such that q divides x. And maybe notice really quick that that means that q is an odd prime. And that's because x is an odd number, so 2 is not going to divide x. Okay, so we've got q divides x, but now notice that that implies that q divides x to the p minus 1. Great, but now that means that q divides the right-hand side of this, because there's some transitivity type property for divisibility. So we've got q divides p minus 1 to the x plus 1. Good. But what that shows us is that we have p minus 1 to the x plus 1 is congruent to 0 mod q. So that's equivalent to this divisibility statement. But now that's the same thing as saying that p minus 1 to the x is congruent to -1 mod q. Okay, good. And so now we're ready to jump into the next step, which will help us build towards Fermat's little theorem, but we're kind of running out of room, so I'll bring everything that we need for the next step to the top, and then we'll continue on. Okay, so since moving on to the general case when x and p were both bigger than or equal to 3, we showed that they both had to be odd. It's clear that p has to be odd because the only even prime is 2, but then we argued that x needed to be odd as well. Then we let q be the smallest prime number dividing x, and we argued that p minus 1 to the x was congruent to -1 mod q. But now let's notice that this implies that q does not divide p minus 1 to the x. Great, and so that's like pretty clear because divisibility is the same thing as being congruent to 0. And so since this is not a 0 over here, that means q does not divide that thing. But since q is a prime and it doesn't divide this exponential of a certain number, that means it doesn't divide the number itself. So we know that q does not divide p minus 1. Okay, great. So now what we can do is apply Fermat's little theorem to p minus 1 and q. So let's go ahead and do that. Fermat's little theorem to p minus 1 and q, where p minus 1 is playing the role of that number a that we had written down in the hints, and q minus 1 is playing the role of the prime. So let's see, that's going to give us p minus 1 to the power q minus 1 is congruent to 1 mod q. Great, and now that's an important little fact to hold on to. So maybe I'll like put it into a blue box. Great, and then we need a couple of more little facts before we get going. And so one more fact that we need is that the GCD of x and q minus 1 must be equal to 1. Okay, so let's maybe talk our way through that. So we know that q divides x, but that means that q minus 1 does not divide x. In fact, it means that their GCD is, they're relatively prime. So I'll let you guys check that. If you have a multiple of a number, so x is a multiple of q, so it can't also share any divisors with one less than that number. Okay, so now what we want to do is apply Bézout's identity, or Bézout's like kind of formula to this. In other words, the extended Euclidean algorithm, to show that there exists two integers a and b that satisfy the following rule. We have ax minus b times q minus 1 equals the GCD, but the GCD is equal to 1. Great. And then another little subtle thing, which I'll say here, but we don't have to like really check carefully. And because I've baked this minus sign into this equation, we can actually take a and b to be natural numbers. Okay, great. So now what we want to do is play some tricks with this number 1 expressed in this form. So now we're going to take the number p minus 1 and we're going to multiply it by 1, but now we're going to use congruences to express this number 1 in terms of an exponent of p minus 1. And the way that we're going to do that is write this as p minus 1 times p minus 1 to the q minus 1. Now notice this p minus 1 to the q minus 1 is congruent to 1 mod q, which means if I raise this to the b power, that's also going to be congruent to 1 mod q. And I should have a congruence here, not an equal sign. Great. So what I've done is I've taken this 1 here, and then I've re-expressed it as something that is congruent to 1 mod q. So this is all like working mod q. Okay, great. Now what we want to do is simplify this with exponent rules. And notice via simplification with exponent rules, we see that this is going to be p minus 1 to the 1 plus b times q minus 1. Great. But now using this right here, which we derived from Bézout's identity, we know this 1 plus b times q minus 1 is equal to ax. So this is going to be equal to p minus 1 to the ax. Great. But we derived on the last board that p minus 1 to the x was congruent to -1 mod q. So that means here we have this as p minus 1 to the x all to the a. But now that's going to be congruent to -1 to the a mod q. Great. Now the next thing that we want to notice is that a must be an odd number, and let's talk our way through that. So we can see that because this number over here, the number 1, is odd. Now q is an odd prime, which means that q minus 1 is an even number. Great. Which means b times q minus 1 is also even. We know that x is an odd number, so that's going to make a an odd number as well. So here we have this term needs to be odd. So in other words, we have that a also has to be odd. Good. But now if we take -1 and raise it to an odd power, we're clearly going to get -1. So this is congruent to -1 mod q. Good. So what we really want to do is look at the extreme left and right hand side of this equation. And notice that we have p minus 1 is congruent to -1 mod q. But that statement is equivalent to saying that p is congruent to 0 mod q. But that's the same thing as saying that q divides p. But now we've got a prime q that's bigger than or equal to 3 dividing a prime p which is bigger than or equal to 3, but that can only happen if p equals q. Okay, great. And now we're like almost ready to say what x is as well. So notice that that tells us that p also divides x because q divides x and p is equal to q. Okay, and then this together with this thing that we haven't used at all, this x less than or equal to 2p, so together with the fact that x is less than or equal to 2p, that tells us that x has to be equal to p. So x equals p. So let's maybe talk our way through that. So p dividing x means that x is a multiple of p. But what are the multiples of p? Well, you've got p, 2p, 3p, so on and so forth. We know that x is less than or equal to 2p, so that means that x can only be equal to p or 2p because it has to be a multiple of p. But we know that x is odd by like an earlier argument, so that means that x can only be equal to p. It rules out its possibility of being equal to 2p. Okay, so we've ended at this spot right here that x must be equal to p. Okay, so now maybe I'll clean up the board and we'll start from that x equals p and see what that gives us. So on the last board, we finished arguing that if x and p were bigger than or equal to 3, then x actually had to be equal to p. And that's actually going to simplify this condition quite a bit. So let's maybe look into the right-hand part of this condition and see what happens if we set x equal to p. Okay, so that means this p minus 1 to the x plus 1 is now equal to p minus 1 to the p plus 1. Great. Now we can use binomial expansion on this p minus 1 to the p type term, and that means we can write this as the sum as k goes from 0 to p of p choose k, and then we're going to have p to the k, and then minus 1 to the p minus k. Great. So again, we're just doing normal binomial expansion there, and then we're adding 1 to this. Okay, great. So the first thing that I want to notice is that the k equals 0 term of this is equal to p choose 0, so anything choose 0 is 1, and then we've got p to the 0, which is 1, and then we have minus 1 to the p minus k, but p is odd, so that makes that minus 1. So we can pull out the k equals 0 term and cancel that with the plus 1 that's kind of also included. So that means this guy right here will cancel this guy right here. And that's going to leave us with this sum as k goes from 1 to p of p choose k, p to the k minus 1 to the p minus k. Great. Now the next thing that I want to do is pull out the first term and then see what we have for everything else. So notice if we pull out the k equals 1 term, we're going to have minus 1 to the p minus k, so that's minus 1 to the p minus 1, but p minus 1 will be even, so that's plus 1, and then we'll have p choose 1 times p, and then we'll have plus the rest of them. So we have the sum k equals 2 to p of p choose k, and then p to the k minus 1 to the p minus k. Great. Now we know that p choose 1 is equal to p, so that means this whole thing right here is equal to p squared. And then furthermore, this whole sum right here is a multiple of p squared, because here we're adding over all of these p to the k terms as k is bigger than or equal to 2. So what that means is we can factor a p squared out of this whole thing. So if we go ahead and do that, we've got a p squared factored out of this whole thing. That's going to leave us with a 1 for this first term. And then for the rest of these terms, we still have the sum k equals 2 to p. We have p choose k. Now we have p to the k minus 2, and then minus 1 to the p minus k. Great. And then since here k is running bigger than or equal to 2, we don't really need to worry about this. This is always going to be a positive power of p there. Okay, good. But now let's go ahead and look at our condition. So our condition is x to the p minus 1 divides this thing. So in this case, this boils down to the condition p to the p minus 1 divides this whole thing right here, which I'll write as p squared, and then maybe I'll just underline all of this in blue and put a blue star there. So that's what we have. And then what's important to notice here is that everything here is a multiple of p. And that's because p choose k is always divisible by p for the appropriate values of k that we have there. So that whole sum right there is a multiple of p. So that means this blue star is 1 more than a multiple of p. So that means it's not divisible by p. So let's maybe notice that. So let's notice that p does not divide blue star. Great. But what that tells us is that this divisibility by p to the p minus 1 lies all within this p squared. So what we have is p to the p minus 1 must divide p squared. Now we're almost done, but I don't want to squeeze it in there at the bottom, so I'll bring that to the top and then we'll move on. So we're almost done. We've just been working hard on the case when x and p are bigger than or equal to 3. So we initially ended up with the fact that x had to be equal to p, and then via this condition right here, the divisibility, that worked down to the fact that p to the p minus 1 needed to divide p squared. So now we're actually ready to go because we know there are only 3 divisors of p squared, and those are 1, p, and p squared. So that means that p to the p minus 1 equals 1, p to the p minus 1 equals p, or p to the p minus 1 equals p squared. So those are our only possibilities given what we know about the factors of p squared. So let's work through these one at a time. So if p to the p minus 1 equals 1, well, that means that p minus 1 equals 0 or p equals 1, but 1 is not a prime number, so that's out of there. Now let's look at this next one. So if p to the p minus 1 equals p, then that means that p minus 1 equals 1. In other words, p equals 2. But remember, in this whole setup, we had p bigger than or equal to 3, and so that doesn't actually work here either. Notice we considered that earlier, and we got the solution 2, 2. Now, if p to the p minus 1 equals p squared, that means p minus 1 equals 2, or in other words, p equals 3. And this actually gives us a new solution, so we're good to go there. And so finally, we have our last solution of 3, 3. In other words, x and p are both 3, giving us this infinite family of solution and then these 2 isolated solutions. And that's a good place to stop.